What percentage of the Earth's surface would have to be covered with solar panels at 100% efficiency to maintain the energy requirements of the United States? Well, solar input is about 1400 watts per meter squared. This is the amount of energy per second, joules per second, per meter squared that impacts the Earth's surface from the sun at this distance. Now we need to know the energy consumption of the U.S., which is, you can look up, is about 10 to the 20 joules every year. And it might give you in kind of BTUs per year, and you need to do a conversion, but this is the value. Okay, so this is an energy per year, just like so it's energy per time, just like watts. So we can convert this into watts, and then if we know we get 1400 watts per meter squared, we can figure out how much we'd have to cover the Earth's surface. So what we have here is we're going to convert to watts or joules per second, and it really is just a conversion. So I leave a space. I put a bunch of multiply bys. Okay, and then we get the units. So year on the top to cancel year, year to days, days to hours, hours to minutes, minutes to seconds. And if I have other empty ones, it won't really matter. 1 year and 365 days, 1 day and 24 hours, 1 hour, 60 minutes, 1 minute, 60 seconds. So I multiply everything on the top, divide by everything on the bottom, and I get something on the order of 3 times 10 to the 12 joules per second, or watts. So if I have 3 times 10 to the 12 watts, and divide that by 1400 watts per meter squared, that gives me 2 times 10 to the 9 meter squared. Notice the watts cancel and the 1 over meter squared goes up. So this is the surface area that needs to be covered. Notice that this is the same as, let's say, if I want to convert this, let's say, to kilometers squared. That means just do meters on the bottom, kilometer on the top, meter on the bottom, kilometer on the top, because I need to get 2 meters, so I have the meters here. So, and this is 1 in 1,000, or 10 to the 3, 1 in 1,000, another 10 to the 3. So we're really talking about 2 times 10 to the 3 kilometers squared, which, if you take a, so 2,000 square kilometers. So if you imagine this as a plot of land, that's only about 44 kilometers on a side. That's smaller than the state of Rhode Island. If we want to do it as a fraction, what we would do is we would find out the Earth's surface. If we know the radius, then we just do 4 pi times the 6.5 times 10 to the 6 meters squared, and that gives me about 5.3 times 10 to the 14 meters squared, and then we can just simply divide and get something that's around 4 times 10 to the negative 4%, which is a pretty small amount. Now, of course, the biggest assumptions here that we're making is that we're getting 1400 watts per meter squared. That's completely unrealistic. We'd have at least a quarter of that just for inefficiencies. And also, where are you going to put solar panels on such a large area? And finally, you have to deal with day and night, and you have to deal with transporting that energy and so on. That's where the costs generally come in. But in theory, one could pretty much offset the entire cost of the U.S. energy consumption with solar panels, provided you wanted to deal with the kind of engineering problem of some area that you cover.